The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The broadcast is now starting. All attendees are in listen-only mode.
Hello, I'm Ryan Phillips, Predictronics Data Acquisition Product Manager and Mechanical Engineer for Predictronics Corporation. From 2009 to 2014, I was a student at the University of Cincinnati, where I got my Bachelor of Science in Mechanical Engineering. Since then, I went to the University of Cincinnati and worked at the Simulation Center and at the IMS Center for about 2 years, followed by where I currently am now at Predictronics Corporation. At Predictronics, I work as a mechanical engineer. I'm the software developer for our Predictronics Data Acquisition Software Suite, and I do most of the measurement and instrumentation work, along with plenty of my colleagues. In the past, I've also done some work on the Predictronics Sandbox Software Suite. So to get started, today we're going to cover several main topics, such as, most of which are listed here, why we would collect data in the first place, some data sources and types of sensors that I'm also going to cover. I'm going to cover a few topics on like what you do with the sensors, like sensor mounting, your data collection hardware. Triggering for when you want to collect your data is also going to be covered. Triggering also affects your data size, because your size does constrain how much data you can collect. Finally, I'll be giving a live demonstration of our Pediatronics data acquisition software suite, and I'll be using it to collect some data from a test bench that is currently sitting next to me. Then I'll just recap a few key takeaways. First thing is, what is data? Data is a measurement of the machine process parameters. The machine process parameter could be something like how far the chuck moves on your lathe, or the temperature of the oil in your reservoir, or many other different process parameters. Data is a record of that over time. This data can be used for a number of different purposes, such as machine health monitoring, process monitoring, fault detection in either the machine or even sometimes in the program, and preventative maintenance. There's more options too. To get started, we're going to cover a few different types of data sources and types of sensors, just to give a brief overview of what's out there. The data sources, the sensor type you're going to want to use depends on your data source. Your data source is, of course, your process parameter. The process parameters can be things like the vibration of a bearing, the current draw of a motor, for example, in a robot arm, or even the flow rate of hydraulic oil through a pipe, for example, hydraulic oil going to a hydraulic motor. Changes in these process parameters will affect the measured data. If it does not, there's some issues with either your data collection or you're not collecting the right data. There are a number of different types of sensors that are used out in industry. Accelerometers are a common one. Load cells aren't as common, but there's also a number of them. Current transducers are very common. Ammeters are slightly less common. Voltmeters, thermocouples, even hygrometers sometimes. Those measure humidity. And microphones, like the current one I'm talking to you guys with, that is a sensor. It measures sound and technically measures acoustic pressure, but measures sound. Accelerometers and load cells measure acceleration and force. They're generally associated with vibration measurements. For example, like measuring your motor vibration that I mentioned on the previous slide, that's an accelerometer. There's two major types of these. There's the charge-based and the IEPE or ICP-based. IEPE stands for Integrated Electronics Piezoelectric, and ICP stands for Integrated Circuit Piezoelectric. I believe one of them is PCB's copyright, actually, but they mean exactly the same thing. Basically, the way an accelerometer works is it has a piezoelectric crystal at its heart, which is mounted to generally the bottom of the chassis, or the housing. And then there's a mass placed on top of that. A free mass is on top of that and attached to the piezoelectric crystal. As the accelerometer accelerates in one direction or another, this mass will apply a force due to Newton's law, F equals ma. The force applied to the piezoelectric crystal causes it to deform due to stress strain. Strain causes on the piezoelectric crystal, creates a charge. This charge can be measured. However, what ICP and IEP do is take the charge and put a small amplifier in the accelerometer with it. That amplifier will measure the charge and then amplify it into a much more measurable voltage signal. The standard charge-based can only go, I'd say, I wouldn't go make a cable for a charge accelerometer beyond like 5 feet. Or you're going to have too much interference from, even in the shielded cable, you'll have interference from radio frequency noise. You'll have just the resistivity of the wire itself is going to cause issues. IEPE, due to the much higher voltage, is not really affected by that, and I've seen cables that have gone over 100 feet without any issues. One thing charge accelerometers do have an advantage on over IEPE is the piezoelectric crystal is, or in some cases, is not particularly heat sensitive. Like, I've seen some charge accels that can go like, I believe, 700 C. or around 1200 Fahrenheit. IEP ones generally can't get above around 250 Fahrenheit or about 115 to 120 C because the the amplifier inside the accelerometer starts having issues with the high temperatures. Accelerometers have a number of different use cases, for example, monitoring the vibration of the motor bearing, or even impact testing, where the load cell will be put in a hammer, and the hammer will strike a test subject, and then accelerometers on the test subject will measure the vibration response. Another main type of sensors that are commonly used in the industrial world are current and voltage sensors. Current transducers will clamp around a single conductor cable. They're almost completely non-invasive. They measure current, unsurprisingly enough. The way they work is they basically have a magnetically permeable coil that measures the electromagnetic flux around the wire. It does require that each conductor be separate from another conductor, so if they're all contained inside one jacket, to use a current transducer, you'd have to split the jacket open and then clamp it around one single wire. You can't put it around the entire cable, 5-conductor cable in the image on the right here. You have to put it on just one of them. If you wanted to measure all 5, you'd have to put a current transducer on each. An ammeter would measure its current flow through the device or the device's shunt resistor. And generally, digital versions will have some kind of voltmeter across the shunt resistor. The voltmeter will have a very high impedance, and they'll measure the voltage drop, and then through that will infer the current. Voltmeters are very common. They measure voltage drop across probes. They do require a very high impedance relative to the test subject because otherwise you'll start having current travel through your voltmeter, which is generally very destructive to it. There are a number of different use cases. For example, we at Predictronics commonly use current transducers to monitor motor load because we don't want to route, say, 10, 20 amps, 30 amps, 70 amps through an ammeter. We just want to clamp around it. We don't want to be invasive. Another type of class of sensors are temperature sensors. There's 2 major types that tend to be used. That's thermistors and thermocouples. Thermistors have a varying resistance with respect to temperature. This can be either positive or negative. The positive ones will they'll either be positive or negative. The positive ones will, of course, change the resistance will increase with respect to temperature. The negative ones, the resistance will decrease with respect to temperature. The accuracy of these things can get up to around 0.1 Celsius. However, as the accuracy increases, the useful range of measurement also decreases. Most of the ones that I see with an accuracy of 0.1 C can only measure generally from around 0 to 100 C. There are many different types of thermocouples. Thermocouples can measure, I've seen some that I believe can get over 1,000 Celsius. There's many different types, such as type J, which is an iron constantan, type K, a chromel alumel, and type T, a copper constantan. Thermocouples work according to the diagram shown on the right in this slide. Basically, 2 different alloys with a junction between them are placed into a medium. The junction is placed into a medium that you want to measure the temperature of, and the 2 free ends are placed into a reference temperature. A voltmeter would then be connected across that, and it would measure the charge that's the voltage differential that's caused as a result of this temperature differential. Thermocouples are moderately imprecise. 1 Celsius is a very common precision that they can have. However, they do have they can have very, very high ranges. Type T, the copper constantan, does have an advantage over others in that the copper junction will not have an effect with a copper wire coming from the voltage measuring device. There are a number of different uses for thermocouples or thermistors, such as measuring the temperatures of an oil reservoir in an industrial machine, or even just a house thermostat. RPM sensors, which are otherwise called tachometers, have another major use in industrial machines for measuring rotating equipment like motors, shafts, and sometimes even bearings. They measure the angular velocity, or the RPM, and there's a couple major types of tachometers. There's laser tachs, Hall effect, and there's even contact tachometers, although I don't see those very often. Laser tachometers work by shining a laser onto a reflective patch that's placed on the rotating shaft. As the patch rotates around, the reflective patch will go through the laser light and reflect the laser light to a photocell. This will create a pulse of electricity that can be measured. However, this does have one minor issue in that grease in industrial settings can commonly block the light, causing the sensor to stop working. Hall effect sensors are invulnerable to grease blocking the light because they do not shine any lights. Instead, they measure the electromagnetic flux as the magnetically permeable medium of the shaft moves by the sensor. However, they require extremely close distances to the shaft. Often they can be a millimeter or less. A few millimeters is generally as high as they go. I think I've seen 7 millimeter ones. All those tend to get kind of expensive. They do also require a change in depth. So if you're measuring a perfectly circular shaft, it'll have the same measurement constantly, so there won't be any pulse train to measure. There needs to be some kind of stud or something placed on the shaft, which is also magnetically permeable, so it'll interfere with the magnetic flux of the coil inside the Hall effect sensor, and that will create the pulse train that's needed to measure it. Tachometers have one major use. They measure shaft angular velocity. Pressure transducers monitor pressure, unsurprisingly enough. They come in two major types, static and dynamic. Dynamic type is a piezoelectric crystal. The static type can measure static pressure head, but doesn't measure very rapid change in pressure particularly well. The dynamic one can measure very high change in pressure, very rapid change in pressure. They can both do high pressure. However, it cannot measure a static pressure head. A piezoelectric crystal requires a constant acceleration or deceleration, changing strain to create the charge. So if the pressure is rapidly moving, like pressure pulses are rapidly going through your pipe, you might want to use a dynamic pressure transducer to monitor those pulse train. However, one thing to note is that they are commonly zero-centered. So you have to know, like, is it 3,000? Even if it's 3,000 psi, it could read zero if it's static. The dynamic transducer will read a zero on a static pressure bed of 3,500 in most cases. There's a number of different use cases for pressure transducers. For example, monitoring hydraulic oil line pressure, monitoring gas pressure in a steam tank. A filter, you can place two pressure sensors, one on either side, and monitor the pressure drop. As the pressure drop increases, you can infer that perhaps your filter needs to be changed. Even a barometer is a type of pressure transducer. It monitors atmospheric pressure. There are other types of transducers and sensors that you may encounter, such as strain gauges, hygrometers. They measure humidity, flow meters, which unsurprisingly enough measure fluid flow. LVDTs and LVITs measure position. Stands for linear variable differential transducer and linear variable inductive transducer. They are for measuring static position. In order to get a good reading of your process parameter, your sensor must be mounted correctly. For example, in the diagram shown on the right here, the base of the accelerometer is not in full contact with the machine. This lack of contact can create attenuations or even amplifications of the frequency domain, which mean that the vibration signal we are measuring is not exactly the vibration that the machine is undergoing. This compromises your data and can lead to invalid predictions. Sensor mountings can be very simple to very complex. For example, in a lab setting where the temperature isn't getting very hot and where there's not going to be any impacts, you could mount an accelerometer to the test subject with simple beeswax. In an industrial setting, you might want to go with a threaded stud or a screw mount and screw the accelerometer on. Magnetic mounts are another method of holding accelerometers or other sensors on. Pressure sensors will generally be threaded because the pressure is going to exert a high force on the sensor, and obviously we don't want it coming out. Hot glue is another common one in lab settings. Even complex armatures exist for things like LVDTs, where both ends of the piston need to be pulled. Armature or something that will connect the two moving components together will be needed. Before choosing the mounting, there's two major questions to ask yourself. For example, one is, how permanent should the sensor be mounted? And how rigidly should the sensor be mounted? The magnetic mount for an accelerometer can be highly rigid depending on the strength of the magnet. Beeswax is not particularly rigid, but is rigid enough for most moderate to low frequency measurements. The armature is obviously very rigid. Threaded studs, which are screwed into the accelerometer and the machine, are very permanent. Beeswax is not permanent, and as such is strong, and again, in a lab setting where you might be moving an accelerometer all around trying to find the best possible position. Calibration is another very important task to do with your sensors. Calibration is the comparison between the values measured by your sensor and a known reference point, or a known reference value. Some examples of this are applying a known voltage source across a voltmeter, or a drop calibration for an accelerometer. A drop calibration is done by having a mass hang suspended from a thread, and then mounting the accelerometer to the mass, and then just simply cutting the thread. The accelerometer will undergo a constant acceleration of 1g, and you can measure the voltage output and then know what the sensitivity of the accelerometer is exactly. For example, a lot of accelerometers are going to be 100 millivolts per G. However, the specific accelerometer might be 101 or even 98.5 or something like that. Sensors should always be calibrated prior to use, and additional recalibration may be required as time goes on if the sensors start moving out of tolerance. There are two different major types of calibration. There's scaling and shifting calibrations. One, the other, or both may be needed depending on your sensor type. For dynamic sensors like accelerometers, you're generally only going to encounter scaling, as in the 100 millivolts per G going to 101 or 98. However, something that's static like the position sensor, an LVDT or LVIT, will commonly have a shift, like zero might not be exactly zero. Data collection hardware should always be checked, is another major topic. You should always check to see if, before buying your data collection hardware, if your data is already being collected. For example, a number of PLCs, for example, on CNC machines, can monitor information like the tool RPM, the load current, what tool is currently being held, the program. And this can save thousands of dollars in sensor and equipment costs if your industrial equipment is already monitoring the information you need. For example, an accelerometer is several $100s. Yeah, a current transducer can be $30, $50. And if your CNC machine is already monitoring that, that's money you save. The data collection hardware is also fairly expensive in a number of cases. Another thing to make sure is to check that your data collection hardware is compatible with your sensors. A number of different sensors will have different outputs and at different levels. For example, a number of sensors will output a voltage, and some will output current. 4 to 20 milliamps is a common output for analog sensors, as is minus 5 to 5 volts, or minus 10 to 10 volts. The data collection hardware obviously will not work if you collect an analog current output sensor to a voltage input module. Even for digital sensors, there are some compatibility concerns. PNP sensors must always be connected to PNP measurement devices, and NPN sensors must always be connected to NPN measurement devices. If you connect an NPN sensor to a PNP measurement module, the PNP measurement module will probably measure nothing because they are simply not compatible. Finally, you should check compatibility with the device to which the data is being logged. Ensure it has appropriate drivers, that it can actually connect to the device. For example, an Ethernet device will require an Ethernet measurement device like an NI CDAC will require that your device to which your data is being logged also be connected to the same network that the measurement device is on. A USB CDAC requires a USB port. That brings us to the next question. When do we actually want to collect our data? And when we want to collect our data is dependent upon the machine state. When is it useful machine state? When is it not useful machine state? Out of that, there's 3 major questions that you should probably ask yourself first, such as, what operating parameter are you trying to capture? How do you expect the parameter to change? And when do you expect the parameter to change? In general, you're going to expect the parameter not to really change too much if the machine is off. So the machine being off is generally a non-useful state. You also will generally not expect the parameter to change if the machine is not really doing anything. So you might not collect data when the machine is just sitting idle. Triggering helps us get that useful machine states. For example, when a roll former is forging a wheel, or when a robot is moving parts, or when a CNC machine is cutting a part. Now, what is a trigger? Honestly, anything can be a trigger. Time, a value of a data channel being something coming from your sensor, value of a feature, honestly anything. This is useful in separating the useful data from the meaningless idle states of your machine. For example, if your machine's program name is not running any program, and you want to measure data when your machine is running a program to machine part A, you don't want to collect data when it's collecting nothing. So you might trigger the data collection when the program being run is machine part A. It aids in comparing like data to like data for prognostics and health modeling. For example, as I mentioned, you don't want to compare part A with part B because they might be completely separate parts. Some basic examples of triggering is one very common one in test world, in research, is triggering off a load cell spike on an impact test. An impact test is where someone takes a hammer, generally with a load cell embedded, strikes a test object, and then measures the response on the test object via accelerometers. It's not useful to collect data before the machine has been struck. The test object has been struck because it's just irrelevant noise. So they'll set up a trigger that says, collect data once there's a major spike on the load cell when the hammer strikes the test object, then collect data for, say, 5 seconds as the impulse response rings down. As mentioned before, you can trigger off a specific machining program being executed by a PLC, or you can even trigger off a machine tool being moved into position, like an industrial robot reaching to grab a specific part. The previous triggers I mentioned were all simple triggers like time or value. However, there are combination triggers which are more complex. These triggers are basically just multiple single triggers linked together via logic gates to form one large complex trigger. For example, in the diagram shown on the right, you only want to trigger when the hydraulic oil temperature is above 75 centigrade and when the RMS of the vibration signal is above 2G. Now, as to why you might want to do this, maybe you only want to collect data when the machine is warmed up and when it's machining. And when it's machining, the vibration goes up, so you say, okay, I'm going to measure above 2G, and once the machine's warmed up, the oil temperature is going to be hot, so only trigger when the oil temperature is above 75 centigrade. Once both those two are satisfied, that's when we can start collecting our data. There's a number of different types of logic gates, and or, not, exclusive or, not exclusive or, not and, not or. These complex triggers greatly increase our ability to collect exactly the data of interest. They allow us to drill down and find exactly identical situations and compare them to each other, which is very useful for machine prognostics. Another major use for triggering is to keep your data size small, because you cannot effectively process, if you collect terabytes of data every single day, processing that is going to be it's just not feasible in most cases. I've seen an information poster basically said about 12% of your data is going to be useful, about 13% is going to be bad, and about 75% is just data that's been collected and is never looked at, simply because there's just too much data to view. With triggering, you can find exactly the information that you're looking for and just not look at information like when the machine is off. Another major concern with high-frequency measurements, for example, if you're measuring at 25 kilohertz on an accelerometer, at double precision, you're collecting 400,000 bytes per second. So 400 kilobytes per second per accelerometer. This causes issues with storage space, because if you're measuring, for example, hundreds of accelerometers, that's megabytes per second of data. And if you're trying to write it all to one single disk, you'll quickly fill up the disk, or possibly even run into bandwidth issues on either the network interface or even the disk bandwidth itself. Now, that might bring a concern. People might be like, how do we solve this problem? Like, we need to collect this data. There is another thing, edge analytics, that can help reduce this data size even more. They can reduce multi-megabyte measurements to just a few dozen bytes of data by computing specific features and values from this data. This might be things like from as simple as a mean to a complex FFT, to a complex windowed blocked FFT vibration processing. This greatly reduces the bandwidth and storage requirements on the device. However, it does require the device you're recording data with to have some kind of processing capabilities to effectively process the mass amounts of data it's receiving. And now I'm going to get into a demonstration using our Predictronics DAC software suite of this test bench, which is there's a picture of which is shown on my screen. It's basically just a motor with a rotating unbalance and a single accelerometer connected to an NI data acquisition device. As basically the way this works is, as the motor turns, the unbalance mounted on the flywheel moves around, creating a vibration on the accelerometer. It creates a vibration that the accelerometer can then pick up, transfer into a voltage signal, goes into the NI module, which is then feeds the data directly to our PC, so we can log this data. So I'm going to Alt-Tab over to our data acquisition software and begin. Now, I've already added the devices. In this case, it's a CDAC 9174 and an NI 9234 module into our software. I'm not going to go through that. That's just kind of mindless busy work. So I'll add a channel group, and then to this channel group, I'll add the channel 0, because as shown here, it goes into channel 0 on the NI device. Add this channel. You can see it's in there. Edit the group. We're going to want the output to be, it's output to this folder. I don't want output to the D directory, root directory. And then we'll also set up a trigger, because right now the motor's off, and we don't want to collect data when the motor's off. So we'll add a value trigger where this value here is greater than 0.001. That's basically 1 millivolt, so it's a very light thing. The motor I'm not turning the motor on super hard. The unbalance is not particularly high, and it's on a fairly good bearing system, so the vibration isn't going to be particularly large. It also means that if I bump the table too hard, it will also trigger. Alright, so we're done setting up our triggers. And we can also do something like, maybe we'll rename this to something a little bit more meaningful, like demo. Alright, and now we should be able to arm it. And that's an old measurement. We'll ignore that. Start the measurement. And let's turn it on. And I'll have to hit plot. Let me actually click plot. For some reason it's not plotting. Anyway, let's restart it, because I don't think I actually started it properly. There we go. And now you can see the vibration measurement is currently being plotted. Sorry about that little hiccup there. And it was waiting in. It should re-trigger in about, I think, 30 seconds, because that's the time delay I have set. So we'll just wait a little bit, see if it re-triggers, which it should, because the device is still running. And there we go again. And if I turn it off, you'll see it just dies down. Alright, so let's stop this. Disarm the data collection hardware. Alright, so some major takeaways from this is data collection is important for a number of tasks, from machine health monitoring to product quality analysis. There's sensors and data collection hardware should always be checked for compatibility and accuracy. You should also always calibrate your sensors. And finally, you're also going to want to collect your data at an appropriate time, so setting up appropriate triggers, and then actually clicking the plot button, unlike me, to prevent logging overwhelming amounts of useless data that must be sorted through at a later time. Oops. So basically, as I mentioned in the presentation, you don't want to collect useless data. 75% of data, people don't even look at it. With triggering, you can find that 25% good data. All right, so that's all. I'll now be answering some questions. Let me just take a look, see if what questions are out there. Questions are currently a little hard to see. Show me a second. Just give me a little second here. What is the difference between a tachometer and a rotating encoder? I believe a rotating encoder is a type of tachometer. I assume that's what you're asking for. I assume what you're talking about is the one where you have a laser light, a photocell, and you have like a disc with the little holes through it. And as that disc rotates, the laser goes through the holes, and then the photocell behind it picks it up. I'm assuming that's the rotating encoder you're talking about, because that is a type of tachometer. Have you guys ever monitored the ground signal in a motor? Generally, we don't tend to monitor the ground because if the ground signal has any kind of significant current flowing through it, generally there's a serious issue, generally something's shorted out. I mean, it could be used if you wanted to monitor whether your motor is shorting out or leaking current to the ground. Oh, you want to monitor the degradation of the insulation in the windings. I mean, it's definitely something you could do. You need a fairly sensitive current transducer to monitor that type of information, like how much current is leaking out. But yeah, it's definitely something you could do. Someone else asked, can you hear me? No, you have to submit your questions through text. You want to predict when the motor will fail. Yeah, that is definitely what, if you wanted to monitor the ground current for leakage currents, yeah, that's definitely something you could do with it. Someone else asked, do you recommend only industrial grade sensors for predictive health monitoring? Generally, we recommend industrial grade sensors because the non-industrial grade will commonly fail if in a factory environment in harsh conditions. For example, to give one brief example of like a factor grade, industrial grade accelerometer will cut smaller, maybe smaller than an eraser head. Does anyone else have any more questions for me today? If not, then I'm going to thank you all for. Oh, someone else asks a new question. Can we get that presentation? Can you send a message to contact? Can you send a mail to contact@predictronics.com? It's on the slide right here. I assume that you can. Oops, someone else asked a new question. What is the purpose of a DAC in the system? Oh, my apologies if I didn't explain that well. The data collection software connects to the data collection hardware and pulls the analog data goes in through a wire software, pulls it from the hardware, and then logs it to some files or a database or wherever. That's what data collection software is. DAQ stands for data acquisition. All right, is there any more questions for us today? Looks like that's a no, so thank you all for joining us. If you want to learn more about Predictronics, you can visit predictronics.com, or you can contact us via contact@predictronics.com. Thank you very much. Have a good rest of your afternoon or morning or wherever you are.